So in this video we are going to discuss the questions which appeared in IIT-JAM 2015. So let's continue with the first question. The statement is a system consists of n number of particles. So that means the number of particles is equal to n, which is much greater than unity. Okay, each particle can have only one of the two energies. Okay, so it's given that the particles can have any one of the energy, either E1 or E1 plus E. Okay, if the system is in equilibrium at certain temperature T, so then we have to find the average number of particles with energy E1. So we can approach this problem by making use of the partition function and then finding out the probability that the particles will have energy E1. Okay, so let's try to write the partition function for this system for one single particle. Okay, that is Z, that is equal to summation Gi exponential minus beta EI. Okay, where I runs from 1 to 2, because here we are having only two energy level. So here, as it's not mentioned what the degeneracy of these levels, so we can take it to be equal to unity. So we can consider these energy levels to be non-degenerate. Okay, so the partition function will be 1, that's G1, and then exponential minus beta for the ground state energy, which is E1. Okay, plus exponential minus beta E1 plus E. So that's the partition function. Okay, now the probability, so let's call this as equation 1. The probability that particle will be in energy state E1. Okay, so this is equal to exponential minus beta E1 upon sum over Gi exponential minus beta EI. Okay, and that is in principle equal to e power minus beta E1 upon e power minus beta E1 plus e power minus beta E1 plus E. So this, after arranging all these terms, this can be rewritten as this is equal to, so we can bring this exponential factor from the numerator into a denominator, and this will turns out to be equal to 1 upon exponential beta E1 minus beta E1. So that will give us exponential 0. So that is 1, and then plus, so then exponential beta E1 multiplied by exponential minus beta E1 plus E. So we will be ultimately left with e power minus beta E. So that is the basically the probability. Okay, so let's call this as equation 2. Now to determine the number of particles with this, the average number of particle with this energy E1, so that is given by, let's call that as N1 average. So that is equal to the number of particles multiplied by the corresponding probability, so which is NP E1. Okay, so which is equal to N divided by 1 plus e power minus beta E. Okay, so this is our answer, that is N1 average. Okay, that is average number of particle with energy E1. So let's see which answer matches. It is C, N upon 1 plus exponential minus E by kt, where beta that is equal to beta is equal to 1 by kVt. Okay, so therefore C is the correct option here. So we are given a situation where a rigid and thermally isolated tank. So we are having a tank, one big tank. Okay, let's try to understand it by drawing a corresponding diagram. So we are having a one big tank which is thermally insulated. Okay, from the surrounding. So let's say this wall is insulated, and this is divided into two equal parts of equal volume by a by what? It's a separated by a thin membrane here. Okay, so and the volume is same for both of the compartment. Okay, and then what is given, one compartment contains 1 mole of an ideal gas A. So here in this compartment, let's say we are having gas A, and in this compartment another gas which is called as B, and N1 that is equal to 1 mole. Okay, 1 mole of gas A, and N2 that is equal to 1 mole of gas B. Okay, so for the two gases, they are in thermal equilibrium at temperatures T. So that means the temperature here it's T, and here also it's T. Both of the gases, although they are different, but they are still at the same temperature. Now if the membrane ruptures, okay, so then what will happen? Suppose this membrane it's broken, then what will happen? The two gases mix. So then the gas molecule A, they will start moving toward the partition on the right hand side, and the gas molecule from the right partition, they will start moving into the left partition. So basically they will diffuse. Okay, assume that gases are chemically inert, so that means there will be no interaction of the gas molecule A and gas molecule B. Then the change in total entropy of the gas on mixing is, so that means we have to find the net entropy delta S total for the system. Okay, so as we have understood from this problem, this process is taking place at constant temperature. Okay, so that means this is an example of isothermal expansion. That's one point here to be noted. Okay, so temperature it's constant. Okay, so which means dt that's equal to 0. Okay, now because both of the gases they are expanding, but they are doing that at constant temperature, and their volume they are increasing from V1 to V2, where V1 is the initial volume which is V, and V2 is the final volume which is 2V, and this is same for the both gases. Okay, so now the entropy change for the gas is given by let's call that as delta S. Let delta S be the respective entropy change when gas is expanding isothermally, and delta S that is equal to dq by T, and from certain initial volume V1 to V2. Okay, so dq by T. Okay, so dq, what is the dq equal to? Because by applying the first law of thermodynamics here, du that is equal to dq minus dw. Okay, for an isothermal expansion, because du that will be 0 because it's an ideal gas. Okay, so for ideal gas, if temperature is not changing, then du will be 0 because the internal energy of the ideal gas it's purely kinetic in nature. So that means what we can do is we can equate dq that is equal to dw, and that is equal to p dv. Okay, so therefore we will make use of this definition or this equivalence between dq and pdv or the work done. So the delta S will be v1 to v2 p by t db, and now pv that is equal to nRT, because n that is 1 mole for each gas, so pv that is equal to RT. So from here p by t will be R by B. Okay, so now if we substitute it here, let's call this as equation 1. Okay, now 1 and 2 implies that delta S for respective gas that is equal to P by T is what? It is R by P. Okay, so P by T that is R by V. So okay, so R, let's take R outside because it's a constant, and then inside we will have dV by V from V1 to V2, and this is nothing but R ln V2 by V1. Here V2 is the final volume and V1 is the initial volume. Let's call this as equation 3. Now we will apply equation 3 for the individual gas, and then we will determine the corresponding entropy change for the individual gas. So let's say delta SA is the entropy change for the gas A. Okay, so that is equal to R ln B2 by B1. So B2 is how much? It's 2B. Okay, so R ln 2V upon V, that's nothing but R ln 2. Okay, similarly entropy change for gas B, delta SB, again R ln B2 which is 2B divided by V1 which is V, and that is equal to R ln 2. So therefore delta S total for the system, delta S total is equal to delta SA plus delta SB, and that is equal to R ln2 plus R ln2, and that is equal to 2R ln2. Okay, so therefore D is the correct option here. A rigid triangular molecule consists of three non-collinear atoms. Okay, so we are given a non-collinear gas molecule. Okay, it consists of three atoms. Okay, which are joined by rigid rods. So that means all these three rods, they are rigid. So when the word rigid is used here, so that means no vibration at all. No vibration. Okay, so that means we can neglect the vibration degree of freedom for this particular case. Okay, so then the constant pressure molar specific heat Cp of an ideal gas consisting of such molecules is, because the four options which are given, they are in terms of mass. So that means here we have to consider the at least a mole of a substance here of the such type of gas molecules. Okay, so let's try to first work out the various degrees of freedom for this non-linear triangular gas molecules. Okay, so if let's continue with the translation degrees of freedom. Okay, so let's note that as Ft. That's the translation degrees of freedom. So Ft, for this non-linear diatomic gas molecule, we will have 3 translation degrees of freedom. Okay, and similarly we can work out the rotational degrees of freedom. Let's note them as Fr, and they are going to be, in this case we will have 3 rotational degrees of freedom because it's a non-linear molecule. So that's why 3 rotational degrees of freedom. And the vibrational degrees of freedom, because it's a, these atoms, they are connected by a rigid rod, so therefore vibrational degrees of freedom will be 0 here. So in total we are having 6 degrees of freedom. Okay, so therefore for one gas molecule, for one such gas molecule, the average energy will be how much? The average energy, if we say that, let's say the average energy per gas molecule, that is equal to the degrees of freedom multiplied by the contribution from 1 degree of freedom, which is half kBt. Okay, so that is equal to 3 times kBt. So this is a situation for one gas molecule. Now for Avogadro number of gas molecules, so that means for 1 mole of a, such gas molecule, for Na, where Na is the Avogadro number. Okay, so then the, let's say U with the average energy, so that is equal to 3 multiplied by the corresponding number of molecules, which is Na Avogadro number, and then N3 Na kBt. So basically we are multiplying the average energy per molecule with the Avogadro number. Now the product of Na and kB, that gives you R, the gas constant. So this is nothing but 3RT. So this is the average energy of 1 mole of a such gas molecule. So let's call this as equation 1. So from here we can determine the heat capacity at constant volume, which is du by dt at constant volume. So this is equal to 3R. Okay, let's call this equation 2. Now because it's an ideal gas, so this will satisfy the relationship Cp minus Cv, that is equal to R. So from here we can determine Cp, that is equal to R plus Cb. So Cb is 3R, so that is equal to R plus 3R, that is equal to 4R. Okay, so therefore here the correct option is C here. As shown in the PV diagram, so we are given a PV diagram. Process A, AB and CD, these are 2 isotherms. So these 2 processes, they are given to be isothermal in nature. Okay, both of them, these are isothermal processes. Basically these are reversible isothermal processes. We are talking about a Carnot cycle. Okay, and similarly process BD and process AC, these are reversible adiabatic processes. Okay, so in this Carnot cycle, which of the following statement is true? So let's quickly revise the important results that we learned during the course in thermodynamics. Okay, so if Q1 is the amount of heat, that is okay, so let me first draw the schematic representation of the Carnot cycle. Okay, so here we are having 2 reservoirs, one at temperature T and another one at temperature T2, such that T1 is larger than T2. So we call this as source and this as our sink. and here we represents this cycle as a the cycle of the working substance basically. Okay, and here working substance, it takes Q1 amount of heat per cycle from the high temperature reservoir, and it ejects Q2 amount of heat to the sink, and at the same time what it does is it does W is equal to Q1 minus Q2 amount of work done. It's external work basically done during one complete cycle. Okay, so now when we go through this problem, so there we encountered one relationship that connects Q1 Q2 and T1 T2, and the relationship is Q2 by Q1 that is equal to T2 by T1, which implies Q2 by T2 is equal to Q1 by T1. Okay, so that is one of the important results pertaining to the Carnot cycle. Okay, now so when this entire cycle occurs, so during the first step of the cycle, that is during the isothermal step, A to B, isothermal process A to B, the working substance takes Q1 amount of heat from the source. Okay, so because source is giving energy to the working substance, so during this step the entropy of the source will decrease. Okay, so that means this point is also true, and the first point is also true as I have written here. Okay, so I think this point is clear. Okay, so during process A to B, the source, it releases Q1 amount of heat to the working substance because the source is providing energy to the working substance. So therefore the entropy of the source will decrease during this step. Okay, so this occurs in step A to B. Okay, now the entropy of the system increases. No, that's not true. So, and let's try to check that. Okay, and okay, I will come to point C at the end. Let's take a look at the point D. Work done by the system, that is W is equal to Q1 minus Q2. Yes, that's true. That's what I wrote here. So W is equal to Q1 minus Q2, and that is true. Okay, now let's check the entropy of the system. So system mean we are talking about the entire cycle. Okay, so let's take a look at the entire cycle, because now the point is that the working substance, it's going through a cyclic process. Okay, so because when a substance, it undergoes through the cyclic process, suppose this is our initial point, and again the final point is again the same. So that means when initial and final point, they converge there at the same point. Okay, so then the entropy change, corresponding entropy change, that is equal to SF minus SI, and that is equal to SI minus SI, and that is equal to 0. Okay, so that means for the working substance, delta S, that is the entropy change during delta S during cycle, that is equal to 0. Okay, so therefore the net entropy change for the working substance during complete cycle, it's a 0. So therefore here only A, B and D, only these three options, they are correct. A, B and D are correct. So let's continue with the next question. The statement is, in the thermodynamic cycle, which is shown in the respective figure here, 1 mole of a monatomic ideal gas, so we are given a monatomic ideal gas, is taken through the cycle A, B, C, A. Okay, here it's given that AV is a reversible isothermal expansion at certain temperature of 800 Kelvin. Okay, so let's continue step by step. So we are given that process AV. Okay, so this is an example of isothermal expansion. Isothermal expansion. So let's write the corresponding parameter for this process. So that means this process is taking place at a certain constant temperature, which is given 800 Kelvin here in the statement. Okay, in which the volume of the gas is doubled. Okay, so it's also given. So let's write these parameters. So T, it is taking place at 800 Kelvin. So that means here TA, that is equal to 800 Kelvin, and what else is given to us? VA is the volume at point A, and PA is the corresponding pressure at point A. Okay, now we can write the identical the parameters at point B, because it's an expansion, so, and it's isothermal expansion, so corresponding temperature will be same at point A as well as point B. Okay, but now the volume, its gas is expanding, so volume at point B, it is twice the volume at point A. Okay, and so therefore to satisfy the ideal gas equation, correspondingly the pressure at point B will be half the pressure at point A. Okay, now we want to evaluate the corresponding energy exchange that occurred during process A to B, because it's an isothermal process, so dt, that's equal to 0, and this implies that du, it's also equal to 0. Why? Because gas is ideal. Okay, and the reason is that for an ideal gas, U is purely kinetic in nature, so that's why it's a temperature dependent quantity. Okay, that's the point here. Okay, so that means we can apply the first law of thermodynamics to evaluate what is the corresponding heat energy exchange. Okay, du, that is equal to dq1 minus dw. Okay, so that means, so because du, this is equal to 0, so this implies dq1, which is the heat exchange during process A to B, so dq1, that is equal to dw basically, and the work done during the isothermal process is given by nr, the corresponding temperature here it's Ta, and logarithmic of, or ln, the final volume that's at point B divided by the initial volume at point A. Now if we substitute these values here, dq1, that is, n is given to be 1 mole, so it's given in the monatomic 1 mole of a monatomic ideal gas. Okay, so that means 1 and then multiply by the gas constant, which is 8.314, and then the corresponding temperature Ta, which is 800 Kelvin. Okay, and then logarithmic of Bb, which is 2Ba divided by Ba, so that will give us 2, a factor of 2, and if you just evaluate this quantity, it will turn out to be equal to 4610.26 joule. So we have calculated the heat exchange during one of the step. Similarly, we will evaluate the heat exchange during remaining steps, and then after, at the end, we will add. Okay, so now let's take a look at the step B to C. Okay, now second part of the question, process BC. Okay, so process BC, this is taking place at constant pressure, so this is an isobaric process. Okay, so for an isobaric process, the pressure at point C, that is equal to pressure at point B. Okay, and that is equal to further PA divided by 2. Okay, as noted in step 1. Okay, and further VC, the volume at point C, that is equal to the volume at point A. Okay, because the point A and C, they are connected by an isochoric process. Okay, and it's given that the temperature at point C, that is equal to 300 Kelvin. Okay, so now we can find the corresponding heat change during the step B to C. Okay, so let's call that as a delta Q, dq2. So let dq2 be the heat exchange involved during process B to C. So that is equal to N Cp and delta T. So N, it is 1 here. Okay, and what is Cp? Because we are given a monatomic gas, so for monatomic gas has only 3 degrees of freedom, so U will be 3 by 2 RT, and then Cp will be 3 by 2 R, and this will gives us Cp of Cp minus Cv, that is equal to R, so that will give us the Cp, that is equal to 5 by 2 R. So you need this information at your hands, only then you can calculate the corresponding dq2. Okay, so Cp is how much? It's 5 by 2 R, so 5 by 2 multiply by R. And what is delta T? Delta T is during process B to C, so that means delta T will be Tc minus Tb, so that is Tc minus Tb. Okay, now if you substitute the value of these all constants here, 5 by 2 multiply by 8.314, and what is Tc? Tc is given as 300 Kelvin. 300 Kelvin minus what is Tb? So Tb is how much? It is written here, it's 800 Kelvin. Okay, so 300 minus 800, that will give us the minus 500, and when you multiply all these quantities, the answer should be minus 10392.5 joule. So negative sign mean heat is liberated during this step. Okay, so let's call this as okay, so this is dQ2. Okay, now the heat energy exchanged during the final step, which is C2A. Okay, so process, that's the third point. C2A processes, C2A is isobaric process. Okay, so in this process, so that means it is taking place at constant volume. Okay, so in this process, let's say that the energy exchange is, corresponding heat exchange is dQ3, and that is given by NCB delta T, and N, because it is 1 mole of a ideal gas, so, and Cb is how much? It's 3 by 2 R. Okay, so 3 by 2 R, and delta T will be temperature at point A minus temperature at point C, that is temperature at final point minus temperature at the initial point. So if you substitute all these values, so we will obtain 3 by 2 R. Temperature at point A is 800 minus temperature at point C is 300 Kelvin. Okay, and if you substitute these values, we will obtain this to be equal to 6235.5 joule. Now the net energy exchange during all these three steps, so that means the net heat exchange during a complete cycle will be delta Q, and that is equal to dQ1 plus dQ2 plus dQ3, and if you add all these quantities, you will obtain a value of 453.26 joule. So this is our answer. Okay, so our answer is 453.26 joule. The question is, 1 mole of a ice at 0 degree Celsius is melted and heated to water. Okay, so let's draw this process schematically, then we can understand it in a much better way. So suppose we are having a piece of ice weighing 1 gram. Okay, so 1 gram, and this is ice, and this is at initial temperature 0 degree Celsius. Okay, and now this will melt first. Okay, it will melt into ice, sorry, it will melt into water, but at a temperature, the temperature will still be same. Okay, so this is a constant temperature process, fixed temperature. So the corresponding heat involved, that we call as latent heat of fusion. Okay, now once this process is taken place, let's say the corresponding energy involved is Q1 here. Okay, during this step, Q1 is the heat required to convert ice at 0 degree Celsius into water at 0 degree Celsius, and then in the next step, the temperature of the water is raised from 0 to how much? From 0 to 39 degrees Celsius. So here temperature is changed, is into water, and let's say Q2 is the corresponding energy, and now the water temperature, it's again 1 gram water, but now the temperature is how much? It is 39 degrees Celsius. Okay, so that means the temperature is changing from 0 degrees Celsius to 39 degrees Celsius. Now what is given to us? The latent heat of fusion, it's given in the statement, latent heat of fusion, because we required that to calculate Q1. So LF is equal to 80 calorie per gram. Okay, and please just remember that the specific heat for water CW, it is 1 calorie per gram, because we also require this information for calculating Q2 here. Okay, and mass of the ice, M ice, that is equal to M water also, that is 1 gram. Okay, so let's say that delta S1 be the entropy change of ice when it's converted into water at 0 degree Celsius. Okay, so delta S1, that is the entropy change when ice converts into water at 0 degrees Celsius. Okay, so delta S1, so this is equal to dQ1 by T. Okay, so what is dQ1, which I have written earlier, Q1, it doesn't matter. So this is the mass of the ice multiplied by latent heat of fusion divided by the temperature at which that process is taking place. Okay, so if you substitute those values, 1 into 80 divided by the temperature, which is 0 degrees Celsius, so which is equal to 273 Kelvin. Okay, and this comes out to be equal to 0.293 calorie per Kelvin. Okay, now similarly delta S2, that is the entropy change of water. Now entropy change of water when temperature changes from 0 degrees Celsius to 39 degrees Celsius. Okay, so that entropy change, let's say that is delta S2, and that is equal to mCW. Okay, and then dq by t basically, so mc dt by t, and when temperature is changing from some initial value t1 to t2. Okay, and this can be rewritten as mCW ln t final or t2 divided by t1. Okay, so here substitute the values of the corresponding quantities. M, that is 1 gram of water, and corresponding the specific heat, that is 1 calorie per gram for the water, and then ln t2, which is 39 degrees Celsius. So this is 273 plus 39 in Kelvin, and divided by t1, which is 0 degrees Celsius, that is 273. Remember that whenever you do the entropy change calculation, don't forget to convert the temperature into Kelvin, otherwise you will not obtain the right answer. Okay, and after solving this will come out to be equal to 0.1335. Okay, now we have to evaluate the net entropy change during this complete process, delta S, that is the entropy change when ice at 0 degrees Celsius is converted into water at 0 degrees Celsius, plus entropy change when water at 0 degrees Celsius is converted into water at 39 degrees Celsius. So after adding these two quantities, so this is 0.293 plus 0.1335, and this will come out to be equal to 0.427 calorie per Kelvin. So this is our answer here. So our answer is 0.427 calorie per Kelvin.